Hi, I'm Daniel Chern from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about a very important invariant in algebraic geometry, that of the Picard group of a variety. So recall that line bundles are very important in algebraic geometry because their sections allow us to create maps into projective space. So it becomes a very natural question to ask, what are all the invertible sheaves on a variety up to isomorphism? Well, the set of these is called the Picard group, and the one thing that's nice about it is it's actually a group, so it has this extra structure. It's not just a set, so it's easier to study. And what this fact means also is that when we want to study this invariant, we have this extra structure to study this variety. Okay, so let's go through what the definition is. We'll start here with X is a quasi-projective variety over our algebraically closed field K. So what is this Picard group? Like I said, what we do is we look at the set of all invertible sheaves, or rather the isomorphism classes of invertible sheaves. And I claim this is a commutative group. So what's the group structure? So I just have to tell you the multiplication, and the multiplication is the tensor product. So remember, when you take the tensor product of two invertible sheaves, they're basically locally free of rank 1. So the tensor product is also locally free, and the rank is going to be 1 times 1, so it's still 1, so it's still an invertible sheaf. Okay, and of course this respects isomorphism classes as well. Okay, so some things to note. Firstly, why is it a group and why is it commutative? So firstly, the tensor product is associative, at least on isomorphism classes. Okay, so you have associativity of the multiplication. It's certainly commutative as well. It doesn't matter which order you tensor these two in. Okay, you'll get the isomorphic thing. So I need to tell you what the 1 is and why there exist inverses. Okay, so what's the 1? The 1 here is which invertible sheaf? It's just the structure sheaf OX. Okay, so remember the OX is just like the ring itself, and when you tensor product over the ring, okay, you don't change that isomorphism class. Okay, so this is going to be the unit inside this group. And the final thing that I need to say is what's the inverse of a line bundle? Okay, so if you have a line bundle L, okay, or invertible sheaf rather, L on X, okay, so what is the inverse? Well, what you do is you just look at the sheaf hom of L into OX. These two are locally free, so of course this sheaf hom is also locally free, and the rank here is also just the product here, 1 times 1 is 1, so this is actually an invertible sheaf. And I claim that it's inverse inside here. So that means that when I take the tensor product of this sheaf hom with the original L, I will get something which is isomorphic to the unit here, which is OX. So I won't go through the whole proof of this, but let me just show you how this isomorphism is set up. So to see why is the tensor product of this sheaf hom here with the original invertible sheaf L isomorphic to O, let me give you this map. Suppose you have F is inside here. It's a section, so we'll work over some open set of X. F is some section of this, and S is some section over that same open set U. Then what do we do? So this is basically a homomorphism from L to OX, and this is something inside L, so you can substitute that into this function. Okay, so you can look at F of S, and it will land inside this O. And you can check quite easily on stalks if you like, or on each of the open sets, that this will actually give you an isomorphism. So probably best on stalks, okay? So on stalks, this is, remember you're looking at locally free rank 1, so this is locally free rank 1, this is locally free rank 1, and you can see quite quickly that this will get you an isomorphism. Okay, so that's rather nice that you have inverses, okay, and that gives us this extra group structure, which is really nice. It makes it a lot easier to study this set and to enumerate the elements in this set and to say what it is. Okay, so let me now tie in to study this Picard group. Okay, the easiest way to do it is to see something geometric. Remember, invertible sheaves are kind of hard to sort of imagine. So the way we'll do that is we're going to use divisors. Okay, and this is something I've prepped up a lot in the previous videos in this playlist. Okay, so I claim that there's a surjective group homomorphism onto the Picard group. What you do is you look at the group of Cartier divisors on X. Okay. And so you have some D here like this, and you send this D to the corresponding invertible subsheaf of the sheaf of rational functions, okay? And then of course I'll put the brackets here just to denote isomorphism classes, just to be a bit more precise, but often I'll leave them out. Okay, so that's great. So that tells you a lot about this, because you have this surjective group homomorphism. Of course, this is a free abelian group. This might not be a free abelian group here. So this will have a kernel. And what is the kernel? The kernel is rather nice too. It's going to be the set of principal divisors. Okay, so it's the set of all divisors of the form divisor of f some non-zero, I should write here, non-zero rational function. Okay, they're called principal divisors. Of course, this is going to be a subgroup. You can see this quite easily. If you have the divisors of f and the divisors of g, then when you add them together, that's just the divisors of f times g, remember. Okay, so that's this is certainly a subgroup of this. And when you do this quotient, okay, you'll get this group. So one way to understand this group is to look at this free abelian group. Okay, if you understand this well, and you understand this subgroup well, you can compute this. Okay, pick x. Okay, let's just see briefly why this is true. So kind of by definition of how we define Cartier divisors, this is going to be surjective. Okay, so the more important thing is that why is this a group homomorphism? Okay, and this is rather nice. Remember, the group structure here is very simple. Okay, it's just because it's this is just abstractly a group generated by prime Cartier divisors. Yeah, I guess a little bit more subtle than that. Okay, so it's going to be a group, and then yeah, so it's a group which may not actually be free abelian. So let's have a look and see why this is a group homomorphism. Okay, so let's look at the group structure here. Okay, so if you have a D and a D prime, okay, you can add them together. Okay, and they will get sent to what on the two sides. Okay, so the one thing that you can do is you can add them together first, and then you can send it over with this what's called the first Chern class map, C1. There are lots of higher Chern class maps when you have higher rank vector locally free sheaves, okay, or higher rank vector bundles. But for line bundles or invertible sheaves, we just look at the first Chern class. Okay, so what is this? So remember, I also said that you can write this as OXD times OXD prime as a subsheaf of the sheaf of rational functions K. Okay, so that's another way. These are actually equal. And now, if you instead send these D and D prime over using the first Chern class to pick x, you get OXD and OXD prime, and the multiplication here is a tensor product. And the point is that, well, this is going to be isomorphic to this one here, so inside here they're going to be the same. Okay. Now, what's the isomorphism that maps from here to here? Okay, so what happens is that, well, you can send this OXD to this K here, OXD prime to this K here. Remember, they're subsheaves of these sheaves of rational functions. And then you can just multiply these two to get you inside the sheaf of rational functions K here. Okay, so it's just the usual multiplication map. We'll map you here over to here. And of course, the image is just this product here by definition. And you can check locally at stalks, okay, that this is an isomorphism. It kind of has to be because it's surjective. Okay, so I guess the other thing is that if you have a surjective map of invertible sheaves, okay, and you're in this setting of varieties, okay, then actually this will be an isomorphism, basically because, well, the rank can't drop. Okay, the rank is lined up so that that always happens. Okay, so the only thing that's left to prove, okay, so we're showing we have a group homomorphism from here, the Cartier divisors on x to pick x. We just need to compute the kernel. Okay, so when do two things get mapped together? So when are two divisors giving us the same thing up to isomorphism here? So when is OXD isomorphic to OXD prime? So this is something that we saw before. Remember, if you have an isomorphism here, it lifts to an isomorphism of the sheaf of rational functions by looking at the generic point. And so, of course, that's given by multiplication by some non-zero rational function. So in other words, OXD prime is equal to f times OXD for some rational function f. Okay, and so that means that if you think about that, okay, so what does that mean? So that means that they differ by this divisors of f. Okay, so that's precisely when that happens. Okay, so that's rather nice. Now we have some way of looking at the Picard group of x. Okay, so let's compute one very important example of a Picard group. Okay, that's the Picard group of projective space. Okay, so the projective space, let's give it coordinates x0 up to xn. And so we'll need some divisors here, okay, to talk about this. That's the easiest way to get your hands on some elements of the Picard group, some invertible sheaves. And so the easiest thing is we'll just pick a hyperplane, okay? So let's suppose it's x0 equals 0, and that's the hyperplane H, okay? So in this case, I claim that the Picard group of Pn is isomorphic to the group, the integers. That's the commutative group it is, okay? So that's rather nice. You can really say what it is, okay? You have good understanding of this group, okay? And in fact, I can explicitly say what the isomorphism, and it's given via the following composite, okay? So first, I take this z, I pick an integer, okay? And I'll map this n to just n times this h. So remember here, Pn is smooth, so all divisors are actually Cartier. Okay, so this is going to be a Cartier divisor, NH. And of course, then we use the first Chern class map to map this over there. So that gives us ONH, and by definition, or one of the many definitions at least, this is what we define as O of n. Okay, or at least up to isomorphism, that's what it is, okay? So here, I claim that this is actually an isomorphism. Okay, so we know it's a group homomorphism, so we just need to check that this map is both injective and surjective, okay? So I don't want to say too much about the injectivity, okay? But note that in the case when n equals 1, we know that all these ONs we've seen before, and they're all non-isomorphic, okay? Because we've actually computed the Hom spaces between any two of these, okay? And if m is bigger than n, okay, there are only 0 Homs going from the OM, the bigger m, down to ON, where n is smaller than m, okay? So that tells you that they can't be isomorphic, okay? So that's what happens on P1. And the thing is that, well, you take any Pn you like, or any big Pn, and you've got this hyperplane, right? So that's going to give, that's your divisor. And if you want to say that these are all non-isomorphic on this Pn, what you can do is you just say, well, if I restrict it to a particular line and they're still non-isomorphic on that particular line, then of course they have to be non-isomorphic, okay? So the thing is that, well, what you do is you look at this H here, and you pick a line that is sort of transversal to this H. So it's not contained inside the H. Okay, and if you restrict to that line, of course, what happens is that this ON on Pn just gives you, so basically you want to allow rational functions which have a pole of order up to n on this hyperplane. And if you restrict to this line here, you allow now rational functions on this projective line, okay, which can have a pole of order up to n at the intersection of that hyperplane with this line. So that means at that point. So that means that you just get ON on P1. And they're non-isomorphic, so hence these have to be non-isomorphic as well. Okay, so that tells you that you have an injective map from here to here. And the only other thing that you need to do now is to show surjectivity. So basically any invertible sheaf that you have here is actually isomorphic to one of this form. So let me show you how to do that, and we'll use the setup that we have here as well to do that, okay? So firstly, note that if you have any prime divisor D on this Pn, okay, it's given by the zeros of some homogeneous polynomial f in x0 up to xn. Okay, so this is some, hopefully a fact that you know, and the basic reason kind of why it's true is that this is a unique factorization domain. Okay, so any prime divisor has this form, and it's a homogeneous, so it has some degree, say degree of m. Okay, so you have some degree m form f in the x0 up to xn, and if you divide it by x0 to the m, that now becomes a rational function on Pn. Okay, so you can talk about what is the divisor of this rational function, okay, and that's going to be a principal divisor. So it's in the kernel of this Chern class map here, okay? So, okay, so what is the divisor of this? So let's calculate its zeros and poles. Well, of course, the zeros of f here, okay, that's going to give you the zeros of what's here. Okay, the zeros of f is just d. This is a prime divisor, so it's a single copy of d. What about the zeros of x to 0 to the m? Well, that's just m copies of h. So you have poles there, so it's d minus mh. That's the divisor of this. And since it's a principal, okay, this is in the kernel of this map, okay, so that tells you that d is linear equivalent to mh. Okay, so any divisor is linear equivalent to mh, any prime divisor, and by taking sums, okay, right, by taking sums, that means that any divisor is linear equivalent to some integer multiple of h. So it's in the image of this map. And there you have it. Picard group of the projective space is isomorphic to Z, and in fact you can kind of list quite nicely all the isomorphism classes of invertible sheaves on Pn. Okay, so that tells you a very good example. So the other thing that we can do is, in general, the Picard group is not easy to calculate. Okay, so one way we can do it, the easiest case is when we have smooth projective curves. Okay. If you look at smooth projective curves, you have an extra technique to try to understand the Picard group, and that's called the degree map. Okay, so let's C be some smooth projective curve. Okay, and suppose you have some actual divisor D on it. So that'll be just some Z linear combination of points P1 up to PR, and let's suppose the coefficients are N1 up to NR. That's a divisor on C. So remember, there's no distinction between Bay and Cartier divisors here. So what's the degree of D? Okay, so this is the definition for the degree of D. The degree of D is just, you just sum up all the coefficients, N1 up to NR. Okay, so that's kind of like the weight, if you like, of this divisor. Okay, so firstly, so we have this proposition, okay, which tells us why this is an interesting concept. Okay, so firstly, the degree map. So you feed in some divisor, and it spits out an integer. So it's a map from div C to Z, and this is a group. And this is a group, and it's actually a group homomorphism. And that's quite easy to see, okay, because if you add two divisors together, what you do, you basically add them coefficient-wise. So if you sum of the coefficients in the total, or the sum of those two, of course, you're just summing all of the, you just add the sums of each of them individually, okay. So this is quite easy to check that it's a group homomorphism if you can't see that straight away. But the more interesting fact is the following. So this is about the divisors C, so that gives you this here. This maps down to Z, but we want to know about the Picard group. And the point is that it actually induces a group homomorphism from the Picard group to Z as well. So in other words, this degree map factors through this first Chern class map to give a group homomorphism from Pic C to Z. Okay. So how does that map work? So what does it mean that it factors through? So that means that suppose you have some element inside this Pic C. Okay, what you can do is, remember, the first Chern class map is surjective. So you can pick some divisor mapping to that element of the Picard group, mapping to that invertible sheaf, that divisor, and you just take its degree. And it doesn't matter which one you pick. Okay, the claim here in the proposition is it doesn't matter which one you pick. You can change it to a linearly equivalent one. Okay, by altering by some principal divisor, you can change it to a linearly equivalent one, but that will have the same degree. Okay, so that's the key point. In other words, the kernel of this degree map here contains the principal divisors. Okay, if that's the case, then the universal property of quotient groups says that it induces a map from the quotient group. Okay, so we want to show that this degree map on this divisors of C in this case, okay, it contains, okay, the kernel of this map here, so it contains all the principal divisors. Okay, so I won't show you this in general. I'll just do the special case where C is the projective line. And in fact, the general case reduces to that of the projective line by looking at maps to the projective line. So for any curve, you can map it to the projective line, okay, in surjectively onto the projective line, and use that to prove this result. Okay, but I'll just do it in this special case here. So the projective line I'll write as a union of two affine lines, one with coordinate Z and the one with coordinate Z infinity. And remember, as I said, using the universal property of quotient groups, you just need to show that the degree of any principal divisor, say divisor of f, is equal to 0. So of course here f is some rational function, non-zero, and we'll write it as g on h. G and h now are polynomials in Z. Okay, so let's just compute what is the degree of this. So I guess we need to work out what is the corresponding divisor. Okay, so let's have a little think about it. So where do the zeros come from? Okay, so firstly the zeros come from, well, G will give you some zeros. So how many zeros does it have inside A1Z? It has degree G zeros inside A1Z. Okay, but what else does G do? Okay, so when you go to, so you want to look on the whole of P1, so we've looked on the A1Z, so there's an extra point at Z equals infinity. If you have a polynomial of degree degree g, like this, okay, then it's going to shoot off to infinity there, so there's a pole. So it contributes also degree g to the order of the pole at z equals infinity. Okay, so that's the effect of g. What about h? H has degree h 0, say. So it contributes degree h poles in A1Z. Okay, but similarly, it will give you zeros at infinity, and the number of them is degree h minus degree h of them. So at z equals infinity, what is the order of the zeros? So this is the number of zeros, and this is a negative number, that means poles. Okay, so at z equals infinity, it will have degree h minus degree g zeros there. And if this is a negative number, that means that the negative of this is the number of poles it has at z equals infinity. So at the end of the day, you do the number of zeros, basically counting the poles as negative. So you add this here to this here, and you subtract this. Okay, so it's degree g plus this term here. So these cancel, giving degree h, and you subtract this degree h, and you get 0. And that gives you the degree map. So that tells you straight away that immediately, okay, if you want to study the divisors on a smooth projective curve, okay, the first invariant that you can attach to it, okay, is this integer called the degree. And this is not just how you just try to understand divisors, but also invertible sheaves. If you have an invertible sheaf, okay, what you can do is you can work out this here by taking a section, for example. You can find this divisor. You just take a general section and look at the zeros of that, and that will give you a divisor, and you look at the degree of that. Okay, so that can often tell you if two invertible sheaves, for example, are non-isomorphic, if they have different degree. Okay, and also means that when you study this, okay, this will also be a surjective map, because you can always map a point onto 1, so this is surjective. Okay, so often you can just look at the degree 0 part, and that's the kind of non-trivial part of the Picard group. Okay, so this Picard group is a very important in algebraic geometry, and I hope you've seen a little bit of how it's interesting and also how to study it. I hope you enjoyed this adventure in pure mathematics.